Welcome again. So this is the last talk for this afternoon before the lightning talks and the poster session. So this talk will be given by Seppelt from Copenhagen, our host city, and we will learn more things on relations between algebraic complexity and symmetry.
Yes, thank you very much for the introduction. And thank you very much for having me. It's a big honor, and I'm a bit intimidated by all these very knowledgeable people in the audience. Yes, so I'm going to talk about lower bounds in algebraic complexity via symmetry and homomorphism polynomials. This is sort of a continuation of the work that Anush mentioned on his last slide. So I'm going to talk a bit more about this. I have some introductory slides, but But I'm going to go over them quickly. So here's my 2 slides of statement that I'd like to convey. So first of all, this is the trivial part of the statement. So every matrix symmetric polynomial can be written as a linear combination of homomorphism polynomials. I guess that's something you can convince yourself of, and I'll convince yourselves of that. And the second part is that these linear combinations actually convey complexity theoretic information. So this is sort of the bottom line of my talk, and I'm now going to make this precise in the next 25 minutes or so. Okay, here's our theorem. We are proving this theorem. We are proving an unconditional separation between 3 complexity classes, symVF, symVS, and symVP. You might not have heard of these complexity classes. This is because we introduced them. So we introduced these complexity classes. This is step number 1. In the second part, I'm going to talk about unconditional symmetric lower bounds, so unconditional separations of these complexity classes. And then in the remainder and most of the talk, I think I'm going to talk about conditional non-symmetric lower bounds that are meant to sort of help us to understand the power of symmetric computation compared to non-symmetric or general algebraic computation. And in the last part, I'm going to talk a bit about the techniques. And I titled this talk, The Miraculous World of Linear Combinations of Homomorphism Polynomials, because this is a very exciting tool and a lot of non-trivial things is going on, and maybe I'm going to be able to convey that. Okay, so let's start with the first part, symmetric algebraic complexity classes. Okay, so yeah, as before, we are measuring the complexity of a polynomial in terms of the size of the smallest algebraic circuit. Here's an example, I guess, yeah, right? Determinant and permanent, you know these two. The first one has polynomial size algebraic circuits. Yeah, okay, you know this. You have seen it on Anush's talk. There's an exponential and unconditional exponential separation between the determinant and the permanent when it comes to symmetric circuits. So this is sort of the starting point. Okay, I'm gonna set the stage again just for all of us to be on the same page. So we consider polynomials in these variables x, I, j, where I and j range over n. We consider matrix symmetries in Anush's terminology. I just call these symmetric because I won't talk about any other types of symmetries. So we're considering the action of the symmetric group on n letters acting on each of these components. So the first copy acts on the index I, and the second copy acts on the index j, and the 2 are independent. So it's like, yeah, permuting rows and columns independently. This is the model of symmetry we are considering. And here's an example of such a symmetric circuit, right? So the multiplication gates involve, for every fixed first index, all second index variables. So if I permute the first index somewhere, I just have to permute the multiplication gates. And if I permute the second index, I have to permute the gates that feed into one of the multiplication gates. So this is a circuit that is symmetric under these matrix symmetries. Okay, good. And I want to highlight that symmetric polynomials, or this type of symmetric polynomials, are actually just functions of bipartite graphs or bipartite multigraphs. So for example, as Anush told you, the permanent counts the number of perfect matchings in a graph. So yeah, to make this even more tangible, so this is a bipartite graph. Always the bipartition is fixed. There's a fixed left-hand side, a fixed right-hand side. Now there are different biadjacency matrices of that graph, but due to the symmetries of the permanent, they both get the same value. So it sort of doesn't matter which of the bi-adjacency matrices I choose, I get the same value, and this is why we use graph theoretic techniques to study these polynomials, because they actually encode parameters or functions of graphs. Okay. So this is the main protagonist of this talk are these homomorphism polynomials. This is our the main tool. So we have a fixed bipartite multigraph F. This is the pattern graph, and N is the number of vertices in the host. Like in the graph, we are counting homomorphisms too, but this is not a graph. Like it's formal variables. And now this Hom polynomial Hom Fn, we sum over all maps from the vertex set of F to the set N. And we pick up all these monomials corresponding to edges in the image, like where the corresponding edges map to. Okay, and I try to make a nice slide, right? So the map is a bipartition preserving map, so we map the left-hand side to the left. Yeah, okay, you don't really see that here. Okay, anyhow, and it's a multigraph, so there might be several UVs that are the same, but it doesn't really matter for the purpose of this talk. Okay. So now the key observation, this is my first, yes?
So here X is a matrix and it's actually 2n, and because what you said confused me.
Yeah, that was confusing, you're right. So the x's are my matrix variables. So I have xij for I and j from 1 up to n.
So h is a function from VF
to n.
N, 2 copies of n, and then...
No, there's only one copy of n.
Preserves the bipartition.
Yes, yeah, but like the way I wrote the h is like the i's are on the left hand side of the bipartition and the j's on the right hand side. Because the h always goes from, so the uv, okay, this is the point. The uv in the product is an order tuple.
Okay.
And the u is on the left hand side, the v is on the right hand side. Yeah, that should clarify it. Yeah, but yeah, this is sort of a technicality, so I think it doesn't matter that much. Okay. So this is the homomorphism polynomial. And now here's my first claim, or the claim that makes the first statement precise. So polynomial is matrix symmetric if and only if it is a linear combination of homomorphism polynomials. So one direction, like the backwards direction, is sort of easier. I guess if you look at this homomorphism polynomial and you just look at the action of the symmetry group, you will see that it is a matrix symmetric. And taking linear combinations of matrix symmetric polynomials preserves matrix symmetries. And in the backwards direction, you have to pick out one monomial of your polynomial and look at its orbit. Under the symmetry group, this would be a subgraph polynomial, so polynomial counting injective homomorphisms. So you get a sum of subgraph polynomials, and then you can change the basis. You can change from the subgraph basis to the homomorphism basis via so-called Möbius inversion, and this gives you this fact. So it's not very hard to show, but somehow what it tells us that sort of if we work on matrix symmetric on matrix symmetric polynomials, all we ever need to care about is homomorphism polynomials. So the surprising thing is that this is actually a useful perspective. Okay. Okay, and yeah, this is just what I just said rephrased. So every graph parameter, and strictly speaking, I mean a matrix symmetric polynomial is a linear combination of homomorphism nodes. Okay. Okay. Good. So here are our complexity classes. I promised complexity classes. So we introduce symVP. SymVP is the class of all polynomials that are computed by symmetric circuits of polynomial orbit size. Again, we use orbit size instead of size because the techniques work for orbit size, and a lot of difficulties dealing with size. And as Anush said, these lower bounds, interesting lower bounds, can already be proven for orbit size, and that sort of makes it the right notion for studying in the symmetric setting. So this is symVP. And then the other notions are, as you would expect, symVS contains all polynomials that are computed by symmetric skew circuits of polynomial orbit size. And the skew circuit is a circuit where at every multiplication gate, at most one of the inputs is not an input. Yeah. Okay. And lastly, symVF are all the polynomials computed by symmetric formulas of polynomial orbit size. Okay, and you should think of these classes as corresponding to classical algebraic complexity classes VP, VBP, and VF. Yes, so the reviewers, we first called symVP, symVS, symVBP. The reviewers didn't like that because there's no algebraic branching program in our definition. In the classical world, VBP and VS, so to say, are the same thing, but in the algebraic world, it turns out that symmetric skew circuits are the the right model for this. This is the thing that worked, and for algebraic circuits there are sort of technical difficulties. So we work with skew circuits, and this is where there's a mismatch between VS and VBP. But that sort of shouldn't matter. Yes, okay. Okay, and I'm going to talk a lot about the relation between these two, these two rows of complexity classes in this talk. You should maybe observe first that these models are a priori uncomparable, right? So first of all, there are non-symmetric polynomials in these complexity classes that just don't fit into the symmetric model at all. And going in the other way, the issue is that we talk about orbit size instead of size. So there are polynomials that have exponential size, but polynomial orbit size and things like this. Yes, but it still turns out that for many interesting examples, these two complexity notions sort of coincide, and this is what I'm going to talk about. Okay, are my definitions are clear? Okay, good. So how to prove unconditional symmetric lower bounds? How to separate these complexity classes? Okay, so as a step towards the separation, so we are going to separate these three complexity classes. We are extending the characterization that Anush told you about on one of his last slides. So in this ITCS paper, we showed together with Benedict that the polynomials in symVP are precisely those that are linear combinations of homomorphism polynomials for patterns of bounded tree width. Right? Okay. Yes, and we extend this to symVS and symVF. The statements are exactly the same, only that you have to replace tree width by path width and tree depth. Yes, and Anush told you that tree width sort of measures how tree-like a graph is, path width measures how path-like a graph is, and tree depth, some people say, measures how star-like a graph is. So these are more and more restrictive complexity notions for graphs. Okay. So this is sort of the main result, and this also requires a lot of work, like going in the upwards direction. Yes, is sort of easy because you look in your favorite paper about Hom polynomials for tree width, path width, and tree depth. There's a dynamic program that proceeds along the decomposition, and you observe this construction is symmetric. And then the linear combinations don't matter, right? Because we talk about orbit size, and each term is fully symmetric. So you can assume that there's no permutation sending one term to the next term. So you can basically take exponential sums in that model. Because it's orbit size, not size. Okay, so this is the upward direction, rather straightforward. In the downwards direction, we use that support theorem that Anush mentioned, and we do an induction on the structure of the circuits, and argue that they compute certain annotated homomorphism polynomials, and you need to set up quite a bit of machinery, but then this sort of works out. Yeah. So this is one of our main results, characterizations of these complexity classes. And now the question is, and this brings me to this miraculous world of homomorphism polynomials, why doesn't that straightforwardly give us a separation of these three complexity classes? So maybe if you know a bit of graph theory, you know that tree width and path width and tree depth are functionally inequivalent. They are different parameters. So you can find graphs of small tree width and large path width and so on. So why aren't these three complexity classes not the same immediately? Okay. So why doesn't this give a separation? And I want to talk about this a bit intuitively, and please bear with me. I think I think my slides are not going to be formally correct, but I think they convey the intuition. So, intuitively speaking, the issue is that we're dealing with spanning patterns. So we count patterns in graphs that are roughly as large as the host we're counting patterns in. And this is a setting that is usually not considered by counting complexity. Okay, so this is the intuitive thing, and then formally this translates to the fact that linear combinations of homomorphism polynomials are not linearly independent. So in the world of counting complexity, this is really perhaps the most important insight somehow, that these linear combinations are unique. You can talk about the coefficients of such a function. This does no longer happen, and this is because we're dealing with spanning patterns. So let me talk a bit about the spanning pattern situation to make this a bit more precise. So I guess, so the problem is that the size of the pattern we are counting is tied to the size of the host we're evaluating, because we have a constant number of variables, or like a fixed number of variables. And just to, as I said, so we all know that K-clique is NP complete, right? But what if the k is tied to n? What happens then? So by the standard reduction from 3 set to k clique, we get that k clique is, or that clique is NP complete if the size of the clique is n over 3 for n the size of the graph. And then you can do padding and get NP completeness for this parameter range for every epsilon, from epsilon n to 1 minus epsilon n. Okay, and you can work a bit more. Okay, and on the other side, if your clique is only of constant size or of size n minus epsilon, then the problem is polynomial time, because you can just enumerate all n to the epsilon many sets, or on the other side you enumerate the complements and you, so the problem is easy. And then you can do a bit more work, so this is under the assumption of NP completeness. There's a result from 20 years ago saying that clique is NP complete in that parameter regime, from n to the epsilon to n to the 1 minus epsilon. Okay, and for n to the log n, we don't expect it to be NP complete because it's just too little non-determinism that we need to use. So yeah, we are not. This is not about deciding the existence of cliques, but this sort of illustrates why there is an issue when you tie the size of the pattern to the size of the host. You get pictures like this. It becomes easy again when the pattern gets very large. Okay. So let's make this sort of more formal. Let's talk about linear combinations of homomorphism polynomials. So the learning should be there are polynomials that have multiple representations in terms of linear combinations of homomorphism polynomials. Okay, and here's the easiest example. We take a product over all I, product over all j, xij. This is an easy polynomial, right? I can fit it into a small gray box, so it should be tractable. Okay, and if you take the standard, however, if you take the standard approach that has been established in this counting complexity world, you observe that this polynomial is the subgraph polynomial for the n, n vertex bipartite, complete bipartite graph. And you can change from the subgraph basis to the homomorphism basis via Möbius inversion. But what you observe is that this linear combination of homomorphism polynomials contain pattern. Basically, it contains the complete bipartite graph as a pattern. And the complete bipartite graph has tree width n, hence path width n, hence tree depth n. So it has patterns that are very complicated. So seemingly, this polynomial is not in symVP. I mean, it's tractable, but it fits into the gray box. So this is the issue. Our theorem tells us, so if we push that polynomial, because it is in symVF actually, through that correspondence we get another linear combination of homomorphism polynomials where the patterns now have constant tree depth, and in particular also constant path width and tree width. I think it's stars, or something slightly more complicated than stars. Okay, so this tells us that this is sort of a difficult object, right? Linear combinations of homomorphism polynomials are difficult to deal with basically because there's no uniqueness. Like you give me a linear combination of homomorphism polynomials and you say, okay, there's a high tree width term, but actually maybe you have given me the wrong linear combination. Okay, so separating these complexity classes actually relies on a long line of previous work. It involves the CFI construction, it involves sophisticated ways of analyzing the CFI construction, and on language that I would call homomorphism indistinguishability, so where we've studied what it means for two graphs to have the same number of homomorphisms over a certain graph class. There's a long line of work. I think you need to cite all of these papers in order to prove the result. And there are a lot of non-trivial arguments in there. Okay, so how do we concretely prove the separation? We look at single homomorphism polynomials. If you just count patterns from one graph, and observe that there nothing non-trivial happens. So for such a family of patterns, this polynomial is in symVP if and only if the tree width is constant, in VS if its path width is constant, and symVF if the tree depth is constant. In other words, a single homomorphism polynomial of large tree width cannot be written as a linear combination of homomorphism polynomials of small tree width. Okay, and this then gives the separation because you can just take single patterns in the respective parameter regimes, and that separates the three complexity classes. Okay. Good. Then I'm going to move on to conditional non-symmetric lower bounds. I still have, okay, maybe I won't manage to do everything, but yeah. So the question is what can our symmetric complexity classes compute? What sort of polynomials are in there? And therefore we look at classical algebraic complexity. And we're going to find that each of these complexity classes contain polynomials that are complete for the respective non-symmetric analogues of these complexity classes. Okay, And we are also like advancing a line of work that goes back to also 10 years, where people observe that specific families of homomorphism polynomials give polynomials that are complete for VBP, VP, and VNP. So people look for natural polynomials complete for these complexity classes and have identified homomorphism polynomials as a source for such polynomials. But these results involve specific families of patterns. So people, for example, looked at cliques or complete bipartite graphs. Then you need to like set certain parameters, and under such choices you get then completeness results for these complexity classes. And we vastly generalize these results by proving this theorem, which looks like a mouthful, but it's not so bad. So if you take a family of patterns, Fn, and some epsilon, if you assume that your tree width path with tree depth is sufficiently large, then your polynomials are hard, first of all, for VNP, VP, and VBP. Okay, and you also need to assume something for containment. So in the VNP case, you don't need to assume anything, because the assumption is in the P family statement above, and for VP you have to assume that the tree width is constant, and for VBP that the path width is constant. Okay, so yeah, basically while this was known for specific patterns beforehand, now just this theorem tells you the same things, but for just following from a general graph theoretic notion for a vast class of patterns. Okay. And you should really think of these, I mean, there's a difference between n to the epsilon and epsilon log n in these two cases, but that's basically, it's sort of the same thing, because you have to, you can observe that if you have a graph of constant tree width, then its path width can be at most log n. So this is sort of the maximal path width that you can achieve, and yeah, maybe one should just take the exponential of path width and define that as path width or something like that. But yeah, so this is not this is sort of natural where this comes from. That's what I'm trying to say. Okay, so how do we prove this? There are two ingredients going into this. So on the first hand, we need like quite sophisticated graph theory that was introduced only a couple of years ago. So we need polynomial graph minor theorems for these three graph parameters, tree width, path width, and tree depth, that are sort of very, very tight. We need very tight graph minor theorems in order to get these forbidden patterns that you need to reduce anything. This is ingredient one, and the second ingredient is that we do we do refinements to a long line of work that develops machinery for complexity for studying the complexity of homomorphism counts. Where similar problems like this were studied in different complexity regimes, so for example in FPT algorithms or for sharp P hardness, and we translate this to the algebraic setting. Some things become easier in the algebraic setting because polynomials allow you to interpolate more things, but some things also become a bit harder, basically because we are dealing with these spanning patterns. So there's basically no room for squeezing anything in if your pattern is too large. So things like this have to be made precise. Okay. Okay. And yes, I'm almost done. I'd like to maybe talk about this in the last and advertise a complexity theoretic framework that is not very widely used, but I think is very useful in algebraic complexity. So there's a question by Sauer from 2016 that we answer: what is the complexity of homomorphism polynomials for sublinear tree width? That was sort of open. I think they proved. I don't actually remember what they proved, but this is the question that remained open. What we saw on the previous slide is that under VP doesn't equal VNP, we can rule out polynomial-size circuits if the tree width is at least n to the epsilon. Okay, and there's another complexity theoretic assumption that is not so frequently used, but very helpful, precisely the right thing here, namely VFPT versus VW1. This is a parametrized algebraic complexity hypothesis analogous to FPT doesn't equal W1 from parametrized complexity. And under this assumption, we can actually rule out polynomial-size circuits for super constant tree width. So the result goes like this. So if supposing VFPT doesn't equal VW1, then the following are equivalent. The tree width is constant if and only if the polynomial is in VP. Okay, and remember, this happens if and only if the polynomial is in symVP. Maybe the implications should be swapped around, like the tree width should be in the middle. So at least for single homomorphism polynomials, symmetric and non-symmetric computation have the same power. Okay, maybe I have 2 more minutes, right? I can.
Oh yeah, okay, 2 more minutes.
Now I can also leave that here for someone to ask maybe as a question. So now this, of course, for single homomorphism polynomials, symmetric and non-symmetric computation is the same thing. But now what happens for the general case, for general linear combinations of homomorphism polynomials? And this is a mystery still, but yeah, there are some partial insights about this. And yeah, thank you for your attention. Thank you very much. Thank you very much for that question, Flora. So there are, so the general case. This is the question: how does symmetric computation perform to general algebraic computation? And yes, so I'm going to rephrase that question in terms of that slightly technical statement. So when is the complexity of a linear combination of homomorphism polynomials governed by the tree width of the coefficients? That is sort of the thing, right? Because for symmetric computation, we get these tree width bounds on the coefficients, and then we would like to prove hardness for polynomials that don't have this. Okay, and here two parameters are very important here. One is the dimension. How many patterns do I have with non-zero coefficient of a certain n? And the other thing I call the volume, which is the size of the pattern. So how big is the size of the pattern compared to the size of the host? Okay, yes. Okay, so what can we prove? So every graph parameter can be put into this box. If you have just a single homomorphism count, if your dimension is 1, then we have perfect overlap of symmetric and non-symmetric computation. So everything is nice. Okay, now the same happens in this graph motif parameter world if the dimension is constant and then the volume also has to be constant. Okay, then extending results of Radu that work for specific kinds of graph parameters. This was extended, or we extended this to this n to the 1 minus epsilon volume in polynomial dimension setting. In the symmetric case, we can go up to exponential dimension. So in these settings, there's sort of no difference between symmetric and non-symmetric computation. And now there's a regime where it doesn't work. So in this parameter regime, we can show that the tree width of the patterns doesn't dictate the complexity. And the white box is open. Right.
Can you give a concrete example for one of these when we don't know? Maybe apart from the one that you, like the toy example that you gave.
So where an example of what exactly?
This red area, something natural in the red area.
Yeah, like these very large cliques. Yeah, okay. Yeah, I think this is the natural example. Yeah. Okay. Thank you very much for your attention.
A couple more questions. Oh, someone has a question.
So you mentioned these connections to these other classes like VP, etc. I was wondering, there is this class which is more recent but less studied, VP space. Do you have connections for this class as well?
I don't know anything about that class, but that's a good point perhaps, yeah. That's maybe something to look into.
Hello. Hi. Does every polynomial which is in VP also is it also in symVP?
Okay, I mean, first of all, formally that question has a limited scope, right? Because, okay. So is every symmetric polynomial that lies in VP also in symVP?
Yeah.
Okay. And I think our intuition is that the answer is no, but we weren't able to construct one. Maybe there's any Pratik just told me about recent progress, maybe Pratik knows anything about this, but yes, so basically, so if you remember these CFI graphs, they cannot be distinguished by bounded tree with homomorphism counts, but there is a polynomial time algorithm for distinguishing them. And now if you would implement this algorithm using a symmetric polynomial in VP, you would do the job. But it's not entirely clear how to algebraicalize this algorithm, and yeah, technical.
Thank you.
So these results you have, they are for bipartite graphs only, I suspect. Is
Yeah.
there anything you can say about the non-bipartite case that follows from this?
Yes, so I think when it comes to these results, this is sort of a choice of technical setup. So you can also do this in the, I think this, Anush, how do you call this? The simultaneous action?
Square symmetric.
Square symmetric. So in the square symmetric case where you have Sn acting simultaneously on I and j, you would need to replace the bipartite graphs by directed multigraphs. Much of this machinery goes through. I think we never worked this out just because it sort of seemed more technical, and this is already very technical. And yes, I think there's something nice about bipartite. Okay, maybe that's not. I mean, bipartite graphs have bounded chromatic number. And that's sort of, this is why you don't have this issue that you can't fit a very complete, you can fit everything in a bipartite graph. Every bipartite graph fits into a bipartite graph. But with a graph without loops, large cliques don't fit into it. So this makes this setup, I think, a bit nicer to study, but I think there shouldn't be any major difference. You just have to figure out the textability.
No, nothing black box.
Yeah.
Thanks.
So in your separation here, quantitatively, like what is the separation? Like is it exponential, quasi-polynomial? Like you just said that they're not contained, right? But
okay. I think they should be as bad as possible. But so what is it? You take for between Vs and Vp, you take the homomorphism polynomial of a complete binary tree, has constant tree width, so it has a symmetric circuit of polynomial into some constant size, and in like the path width is logarithmic in the size, in the number of vertices. So yeah, so this is an n to the log n. Yeah, it should be quasi-polynomial, right? N to the log n. But I think it cannot be better somehow. I think that is.
that is the.
Yeah.
So all of these are tight separations that you get.
I think so. Yeah.
Thank you.
Do they have complete polynomials?
Concrete polynomials.
Complete.
Complete polynomials. So yeah, I think the beginning of this project we thought about symmetric reductions and notions of completeness, but it was sort of difficult. And then since you can prove unconditional lower bounds for interesting polynomials, we stopped looking into. I mean, this is something
Can I add something?
you can. Yeah, of course.
Yeah, I think there is some update. So I think now we have a notion for completeness. So, yeah.
Okay.
So about symVNP.
Yeah. This wait for the next coming on. No more questions.